In chapter 1, you have learned that any real number you can represent them and mark it on a number line. So you can have a positive number on the right side and negative number on the left side. But if you are given a complex number, minus 7 plus 3i, how can you present them visually, on a number line? How? Assalamualaikum. Hi, I'm Kak Dr. Kat. So in this lesson, you will be able to map complex number on Argand diagram. So what is Argand diagram? So Argand is a name of a Swiss French mathematician. So here is a Argand diagram where you have the feature of the Argand diagram is the imaginary axis. So this is wrong. So imaginary axis on the y part and the real axis on the x part. So any real number can be represented as a point on the Argand diagram. Okay, Argand or Argand, I don't know. So this is a French Swiss mathematician. So I call it as the Argand. Okay, so that you have a complex number as x plus iy. So the x part is the real part is on the real axis and the imaginary part on the y-axis, so that you can have a coordinate of x, y. So from this point, actually you can connect the origin to the point, so that it makes an angle of theta. Uh, Therefore, you can see that it form a right triangle. So if you have a right triangle, so that you can use hypotenuse, that means you can use a trigonometry to solve any problem which is related in a Argand diagrams. That means this complex number is can be connected with the trigonometry. So from that property, you can have the distance here is equal, the square of the distance from the origin is equal to the x square, x and y square. All right. So what is theta? Theta is the angle. We call it as an argument of z. So this is the argument of the complex number, or we can write it as arc z equal to theta. And theta can be in radian and in degree. So but make sure if you are in degree, make sure that you have, for example, 45 degree. You have to put this degree to indicate that it is the degree. Okay, and then you have the argument, and then you can have also a modulus of z, the modulus of complex number. The modulus of complex number is equal to the distance from the origin to that particular point, where it comes from the first property here. Okay, the modulus is written as the lines, that the bracket over there. So don't use this bracket, don't use this bracket. Use this straight bracket to represent the modulus of the complex number, which is the modulus of complex numbers is always positive because it is a distance. So it is always positive. Okay, it is distance from the origin to the point. Okay, and then for example, in the field of electronics, so they usually use what we call angle notation. So angle notation is written as the modulus and the argument. Okay, this is the notation. So you may see this in commonly in electronics field. Okay, so let's have an example. So you have given the complex number 3 plus 4i. Then the argument of z is 0.93. How we can get it? Okay, so you can make a tan theta equal to 4 divided by 3. So you will get theta equal to 0.93 in radian. Okay, the modulus of z equal to the distance, which is the hypotenuse of this triangle, is equal to 5, and another complex number notation, which is in the angular notations, it is all written 5. The argument is 0.93. So let's look at the conjugate of the complete number on the Argand diagram. So the conjugate, for example, you have a 3.4i, so that the conjugate is equal to 3 minus 4i. Okay, so 3 minus 4i, the conjugate of the complex number is actually the reflection on x-axis. So it is located here. Okay, so visually, the conjugate of a complete number is a reflection on the x-axis. Okay, so it reflects at x-axis, and then the modulus of the complete number and the modulus of its conjugate is the same because the hypotenuse is the same. Okay, same the number. So argument is direction sensitive. Okay, so that means the conjugate is, for example, in chapter 1, this is positive theta and this is negative theta. Okay, so these are properties of the modulus or involving complex number and its conjugates. Okay, right? Okay, so this one is usually in quantum mechanics. For example, the wave function multiplied by the conjugates. This is equal to the psi squared. This is always can be seen in quantum mechanics. So these are others properties of modulus. So modulus representing the distance from the origin to the complex number. Okay, so let's look the parallelogram law of addition. So when you add two complex number, it can be represented as a parallelogram in a Argand diagram. So for example, you are given two complex numbers, z1 and z2. So when you add them, you will get the imaginary part plus the imaginary part. Okay, this is normal. Visually, as in a Argand diagram, so if you plot the first z1 here and then z2 here, for example, so the addition will be here, located here. Okay, when you make the modulus line, okay, from origin to z1 and origin to z2, so you will see that the x1, okay, plus x2, so you will get this position for x, and then y2, y1, so you have this. So the addition of z1 and z2 will build a parallelogram. Okay, so for example, let's put a value 1 plus 3i and then 4 plus 2i. So you see this is 5 and this is 5 also, so same. Okay, so you can see that the addition of the two complex number will be at the edge of the parallelogram. So let's return to the teaser. So you are given negative 7 plus 3i. So this can be represented as this is the negative 7 on the real part and then 3 on the imaginary part. So you can present z on the number line, but you cannot use the number line. Now we use a Argand diagram where it involves two dimensions. So a number line is just one dimension, but since it is a part, it has an imaginary part, so it has a two dimension, real part and imaginary part. Okay, so we'll meet again in the next lesson involving polar form. Okay, bye.